Okay, so we are talking about DC to DC buck converter. If you remember the application of mobile charger, right, and this is something which we have been looking upon at again and again. So you have an AC voltage and then you have a rectifier bridge, a full bridge rectifier followed by a capacitor, right. So if you have 230 volt AC here, this kind of circuit would give you, if you use a very large capacitor, this would give you a voltage here which will have small ripple, something like this, and whose more or less average voltage will be 230 into root 2, which is about 325 volts, right. So in your adapter, in your mobile charger, the first stage is this rectifier stage which gives you 325 volt, and then you use this 325 volt and you want to step it down to 5 volts, right, because 5 volt is the one which is coming out of the pin which goes to your phone and charges your phone. So you want to step it from 325 to 5 volt, right. How much is that ratio? 325 by 5, how much is that? How much is that? 65. So you want to attenuate the voltage by 65 times. Okay. Now the question is, can you use a buck converter to do this? It's DC to DC, reducing voltage, right, from going from one DC voltage to another DC voltage. Can you use a buck converter to do that? Yes, we can, right? Whatever information we know as of now, it seems possible. Why not? I mean, correct? What will be the duty cycle? What will be the duty cycle? How much? It's 0.00 करके बताओ यार. 0.0154. Okay, fine. So this would be your duty cycle, right? Let's say we are switching at 500 megahertz. Let's say our switching frequency is not 500 megahertz. Let's say our switching frequency is 1 megahertz. Right, so we are switching at 1 megahertz. What would be D times TS? Can someone calculate what would be D times TS? So TS is 1 by switching frequency, 1 by 1 megahertz multiplied by duty cycle. It will be 15.4 nanoseconds. Okay. Good. So when I came to class, somebody was talking about some nanoseconds, microseconds. What was that? Microseconds. So what was that? How much? What was the value and what was that microsecond for? Okay. And how much was that? 24 megahertz was the clock crystal, right? Yeah. So when you, all of you are doing microprocessor course, right? So if 25 kilohertz is your crystal frequency, then inside the microcontroller you would have some kind of a PLL or something which would step down the clock frequency, right? So your execution, assuming that it's 1 to 1, you can execute one instruction, one micro instruction maybe at every how much microsecond? 1 microsecond? 1 microsecond? Roughly one instruction, half microsecond. Okay, fine. Now you see this value. Now if I am using my same microcontroller to generate this duty cycle, right, which means that I want this, right, and this thing is the main thing, and I really want a very high precision D into TS, because if this is 10% off, my output voltage will also be 10% off, right? If this is double, my output will, instead of 5, you will get 10 volt, right? So you realize that creating this very small time pulse of a very precise value is very, very challenging if you are using a microcontroller, the one which you have been studying in the other course, right? So that is the challenge number 1, right? That's the problem if you want to do from 325 to 5 volt using a buck converter. Yeah, that we can do. So we'll come to that. Talk about? Yeah, we'll come to the solutions part. We'll come to the solutions part. Let's first see all the list of problems, right? There are more. This is just one. So, can buck be used? Of course, we know the answer would be no. But first reason is resolution of pulse width modulation, right? The resolution of this duty cycle or the resolution of the pulse width modulation. That is going to be a one practical challenge. Of course, theoretically you can do it, but practically, you would have to use a very high-end processor, or you can shift to analog control, which is also, of course, a possibility. But if you are trying to do it with the digital microcontroller, it's going to be a challenge of generating a pulse precisely of a very, very short duration. All right. Second problem. Let me quickly draw a buck converter. Okay, this is a buck converter. Now, let's say this is your 325 volt and this is what you want is 5 volt. Assuming your inductance is very, very large for the time being, right? What would be the switch current IS? The switch current IS, now if in this case the duty cycle is very small, right? So this switch is closed for very, very short duration. So this switch current will be like this and then off, sorry, and like this and then off, right? That's how the switch current would look like, right? If I am feeding, let's say, X power, right, and assuming this is ideal circuit, there are no losses, then the average output power is same as average input power. So 325 into average of this current is some value which I have to maintain, and that average would be somewhere here, right? So if you would have been going from 325 to let's say 200 volt, right, this width would have been substantial. For the same average value, your height would have been much, much lower. Is that okay? If you are comparing the two cases, 325 to 200 versus 325 to 5 volt, in case of 325 to 200 and the same output power, same input power, so your average current is the same input side, switch current, so the peak current of switch will come down substantially. Is that okay? Because of that, that means if you want to do a buck converter with a very low attenuation, you require a switch which should have a substantially large peak current handling capability, right, as compared to if you want to buck only 2 times. If you want to buck 65 times, you require a switch, semiconductor switch, which is usually defined in terms of the current requirement and the voltage requirements, right? So voltage requirement, it has to block the same voltage, but then the current requirement, peak current requirement is very large. So is the RMS current requirement. Again, since the peak is more, the average is the same, but the RMS of this peaky waveform would be much, much higher. All of you agree, right? You find the RMS of a voltage with the same average, the RMS value would be much, much higher, right? Okay. Anyone wants to answer it? What he's saying is RMS current of the switch should be equal to the RMS current here and not the average currents. Okay. Anyone who wants to answer that? So what I'm saying is that in this case, the average currents input and the average output, if you are assuming some average output power, let's say the average output power is, for example, 5 watt, right? So what I'm saying is this average current will remain constant and it will equal to 5 upon 325. Will the average be constant or will the RMS be constant if I keep, reducing the output voltage, maintaining the same output power? Anyone? Should I repeat the question? My output power is fixed 5 watt. Output voltage, I have two options, 200 volt and 5 volt, right? And the input is the same 325 DC voltage, right? In these two cases, would the RMS switch current be same or the average switch current be same? How many of you say average switch current be same? 1, 2, 3, 4, 5. Okay, how many of you? क्या हो गया? What is average and RMS? I asked for average first. And so average would remain the same, right? Question is why? Because what is the average input power? Voltage into current into integral dt 1 upon Ts, right? That's how you find the average input power. Na? We are saying efficiency is 100%, everything is ideal. If this is constant, you can take it out of the integral. So what remains in the integral is nothing but the average current, right? So the average current remains the same, and therefore if you are creating 5 volt, your RMS current is becoming very, very large. The average is still the same, but now the switch you would have to use here should be capable of handling large RMS current and also the large value of peak currents. So therefore it may not be an optimal solution in terms of cost to really produce 5 volt from a 325 volt source. So second thing is large I peak and I RMS of semiconductor devices. Is that okay? Yes. No, for 200 volt output, your duty cycle will be reasonably good, right? So this width would be substantial. So of course, if this width is substantial, the peak value will come down because the average is the same, right? Any questions so far? Okay. The third problem, which is from the same logic, is that if your RMS currents in the switches are high, because these currents have now become like peaky, right? The losses that will happen in the switch, assume there is a small resistance here. What will be the loss? I square R. It will not be the average current multiplied by the resistance, right? Losses is I square R. If I have a wire, a current is flowing. If I am flowing a sinusoidal current, average current is 0, but still you have losses, which is I square R, right? So your losses become substantially high. So your efficiency of this conversion becomes low. In other words, your heat dissipation will be more. Your charger, would get absorbently high heated up. You may not be able to package it in a very, very small form factor. So efficiency reduces, right? These are the three main reasons why somebody would not use a buck converter from going from 325 volt to 5 volt. We are not quantifying the other two factors again, because this is still a basic course, but subsequently you can quantify these things. You can see efficiency would be like really, really poor. I mean, it will be so poor that you would think that I could have done a linear regulator instead of doing a switching regulator, right? But we are not finding the values now, but you understand why that would be poor, right? Any question? No questions? Okay. What is a linear regulator? What is a linear regulator? It's kind of voltage divider using a MOS instead of a resistance. So that MOS will operate in the saturation region. It will act as a current source multiplied by the load resistance and give you the voltage, right? Any question? Okay. Then this is the story about buck converter, where we don't want to have a very high attenuation. Similarly, if you talk about boost converter, you cannot, if you want 5 volt to 325 volt now here, right, which a lot of applications would require, not exactly the same but some other stepping up, but if the gain is very, very large, you would still be facing same problems with boost converter also. Problem number 1 would remain the same, right? VO by V in is 1 upon 1 minus D. right? So if you want very large gain, right, your duty cycle should be very close to 1, correct? So again you have to very precisely control that it should not be 1, it should be just less than 1, and how much less than 1 you have to very precisely control. So you need a digital, if you are doing digital control, you need a precise control. Your RMS currents in the switches would go up with the similar logic, right, because of which you would require semiconductor devices of higher capability. Your losses will also go up, your efficiency will also reduce. Therefore, the basic buck and the basic boost, we never use it to provide very large gains. Is that okay? There is one more problem with boost converter, and let me just quickly tell you about that. Or if there is space here, let's just use this space itself. Anyways, I would need space. Right, so if you want to do boost hypothetically from 5 volt to let's say 500 volt, then one would not use a normal DC to DC boost converter. And the reason number 1, 2 and 3 we have already seen. There is one more reason, 4, and that reason is as follows. Let's say you want to do 5 volt to 500 volt. This is your inductor, this is your switch. Alright. So, in ideal case, the output voltage is equals to, output voltage is equals to input voltage upon 1 minus D. Right? This is the ideal equation which we have derived in CCM, in continuous conduction mode, right? So, if you want a very large gain, that means your duty cycle should be very close to 1, and then you will be able to get. So, if I have to plot this equation, if I plot duty cycle versus the gain is VO by Vin, right? When D is equal to 0, this is 1, and as D increases, this would, go like this. Of course, D approaching 1 would be like really steep slope, correct? And that also shows us that a small deviation in D could change the output voltage substantially, right? And that's the problem number 1 with the microcontroller precision. But this is how the output gain versus duty cycle would look like, right? D going from 0 to 1 for an ideal equation. Now this is what we are, something which we are not really deriving, but you have to, for now you have to accept it. If you add a small resistance in it, right? If you add a small resistance in it, and you can still do the derivation, but we are not doing it in this class, you can do it in your advanced power electronics courses. This expression changes, and this expression becomes, okay, which color is not visible? Blue is visible, blue is not visible. I don't have any other color, so we still continue to use. Right, so if you consider small resistance in the inductor, then your expression changes to this expression. You have an extra term here in the denominator, right, which was earlier not there, because the small r is this series resistance, inductor of the resistance, the capital R is this shunt resistance, right, the load resistance, and D is the same duty cycle. You can derive it, but we are not deriving it now. But if you see what this presence of this resistance does is transform the relationship to this, and because it transforms the relationship to this one, and which is the real expression, your curve between gain and duty cycle changes. Your curve between gain and duty cycle changes, right? At D equal to 0, what is the output voltage equals to? it will be Vn upon 1 plus R by R, right? Typically, this is series resistance of the inductor, it would be in milliohms. This is the load resistance, it could be few ohms. So if you divide 1 milliohm by 1 ohm, you get 0.001, right? Very, very small. So more or less you get output voltage equals to input voltage. So you are at the same point, but as you go further, this is how the graph becomes. Right? It sort of gets little bit lesser as it keeps following. If D approaches 1, what would be the output voltage? If D approaches 1, what would be the output voltage? बता हाँ क्या जीरो so जीरो क्या why will it be zero? अच्छा ठीक है okay. So if D approaches 1, your gain becomes 0. So this is what happens in real life, right? So because of this small resistance which is always present, you cannot achieve a very large gain. You cannot achieve a very large gain, right? So in boost, the gain is limited. So even if you say, okay, forget about efficiency, I don't care, I will buy the most expensive microcontroller possible, I'll buy the big devices, still you cannot achieve a gain as big as 65, in this case maybe 100 or something, right? You cannot do that. Practically now, this peak value of the gain, which is the maximum gain, right? This is the max gain. The max gain is dependent on small r, capital R and so on, right? So there is no fixed answer to it, but if you ask me practically, boost converter, what are the gains they operate at? So usually, maximum they go is up to 3, 4, maybe in very extreme cases I have seen somewhere 5, but I have not heard usually of a boost converter going beyond that. Yes. So and 5 is also actually a bit uncommon. Most of the application you would see maximum goes up to 4. So if you have to put a value, you can put let's say 3 to 5 here, which are like sort of more experience based values, but that is it. You cannot have a gain of 100 from a boost converter. So it's not even theoretically possible. Forget about the performance degradation. Any questions so far? Okay. Then what do we do? How does your phone charges from the 230 volt supply? How does that happen? Okay. 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 You can do that. What he's saying is that once you rectify, let me bring back this board. Once you rectify, you can place a inverter again, right? And now you create a very high frequency voltage, then you put a transformer again, then it will step it down, then you put a rectifier again, and then you would get a low voltage. Yes, that's a way. And we officially have name of these sort of converter topologies, right? So there are different ways you can use the same transformer which we have used previously, but now those transformers are not seeing low frequency, they are seeing very high frequencies. And there are various circuits, like we saw 2 circuits, buck and boost, which didn't have transformer, but there are various circuits which are using those transformers to do the overall buck and the boost action. So now we'll see 1 or 2 of them, right? Basic principle is the same, right? Somehow we'll try to invert, or somehow we'll try to, create a very high frequency AC voltage, give it to the transformers, transformer will do the step up or the step down function, and then we'll rectify it. but there are different ways in which you can invert, there are different ways in which you can rectify, and therefore there are lot of topologies, lot of circuits possible, right? We'll see some one or two basic ones as a part of this course. Yeah, so by the way, the cascaded topology would also not work. Now you can make it out why. If you are doing boost, 5 times, 100 times jaane mein, you have to do 5 into 5 into 5, right? You can imagine, I mean, it will be unnecessarily wastage of lot of resources. If you do cascaded buck also, again, you would not really use a buck for a very large gain because the efficiencies would be very poor. So you would do 3-4 times buck, then again 3-4 times buck, and it just doesn't make out. So what works is using this transformer somewhere in these circuits, right? Now you would say if you are anyways using transformer, just put a transformer here, right? And then forget about it, isn't it? If anyways you have to put a transformer here, and that will step down 230 volt to, let's say, 3 volt RMS or something, then you rectify, you will get a 5 volt, and that's it. Use it, na? You don't even need a buck converter, you don't need any converter at all. So let's say our option 1, use transformer. You have to anyways use transformer, but the option 1 is use transformer in input AC, right? Now you have you may not have seen these kind of adapters, but I have one in my home. I could have bought it. So this is actually a Casio or piano, which is pretty old, and that came with a power supply, an adapter, which gives a 12 volt output. But that adapter, if I see, it's quite heavy. Not like the mobile phone chargers or adapters which are really lightweight. This one is like pretty heavy, and then it gets heated up also. And this is what is done in that, right? This is what is done in that. So any reasons why this, if I use this solution, it's going to be heavy? Why is that? Correct. So we understand the transformer basic equation, which is E equals to 4.44 NF phi m, right? So if your frequency is 50 hertz, everything else is the same, your flux is going to be X. If your frequency is 1 megahertz, your flux is going to be how much? Same factor, right? 1 megahertz by 50 hertz is how much? 1000 by 50 is how much? 1000 by 50 is how much? 20, right? So 20,000. So that means your flux will be 20,000 times more if you use it as 50 hertz transformer versus if you want to use it, I want to create a 1 megahertz transformer, isn't it? So your overall size of the transformer becomes smaller if you operate it for very high frequency. That is something which we have learned in the previous course also. And therefore you can do this, nobody stops you, put a 50 hertz transformer here, right? And it is what was done actually 10 years, 20 years before. The only thing is the size would be substantially big, right? And the other thing would be, so if I put a transformer here, right, the size of this transformer is going to be substantial. You may not be able to carry the mobile charger in your pocket. Second problem is that now even if you use a transformer, this input voltage may not be exactly 230. It will change, right, depending on different time of the day, different location. So you may not get exactly 5 volt here. You still need some amount of control, right? You may still end up putting either a buck converter or a linear regulator, right? In those days when I'm talking about these big bulky adapters, it used to be a linear regulator here. So after this, you would put a linear regulator. So you would put a device in the series and then load resistance, right? And this would cause losses, and therefore those big transformer based adapter used to get heated up also substantially. Is that okay? Yeah, so this is very much practical. 20 years back, nowadays nobody would do it, doesn't make sense. So we'll go for option 2. What is option 2? Option 2 is we still use transformer, but we use transformer at a very high frequency, right? So high FS transformer. Alright, go ahead. Yes, the reason was size was this low frequency transformer. The reason for heating was because we were not using buck converter, we were using linear regulators to regulate the output voltage. By the way, anyone has seen these kind of adapters at your home? Maybe your any old electronic gadget you have at home, you might have seen this. No? No one? You have seen it? Where? It's a old? But for what application? 220 to 110 volt might be step down transformer or something. Yeah. That is more like a step down transformer. May not have a DC output, no? It will be only AC to AC. So that is possible. Anyone else has seen anything of this kind? No one? Heard of it? Okay. In this class? Okay. Where did you hear this? Okay. Got it. Okay. All of you remember the transformer now, right? Because we are going to use it. So you remember transformer? This is an ideal transformer. Do you remember the dot conventions? Do you remember the dot conventions? This is an ideal transformer. At any point, if this voltage is positive and negative, if this dot is positive, the other dot would also be at a positive voltage, right? That was the dot convention. If you don't remember it, just go back and just flip your previous semester notes and just quickly, sort of revise this part. This is the ideal transformer, right? Wherein if I apply an AC voltage here, the same AC voltage would come there multiplied by the turns ratio. And if the dot is positive here, the dot will also be positive there. Alright? But in real transformer, you have few more components. What are those components? Let's now try if you remember it. What are the additional components in the equivalent circuit of a actual transformer? One by one. Cool. Resistance to show the copper losses on both sides, right? Winding losses. Okay, what else? Leakage inductance on both sides. Magnetizing inductance and the core loss resistance, which represents in a way for our equivalent circuit both hysteresis as well as other core loss eddy current. Okay. So all of you remember this equivalent circuit, right? We are going to use it now and we are going to build power electronic circuit using the same transformer. Okay, I'll just erase this one and then we start drawing the circuit. Okay, by the way, before we do that, before we start seeing the circuit, there is one more advantage of actually using transformer. Hypothetically, even if it was possible to do a buck converter, right? Even if it was possible, let's say hypothetically, to not use a transformer, directly rectify and then use a buck converter, there would have been one problem. Can anyone guess what was the problem? Yeah, but what would be the problem? What would be the problem? Yeah. So my question is that hypothetically, let's say we use buck converter and somehow the buck converter is reasonably efficient for stepping down from 325 to 5 volt. I don't care about other things. There is no transformer here, right? So I have an AC voltage, rectify, create 325 and then step it down to 5 volt using a buck converter and then use it to charge your phone. Is there any problem? Is there any problem? Of course, if the switch fails, the circuit fails. Any other problem as a user you might encounter? Forget about, let's say you don't know power electronics. As a user, do you think you might encounter any problem? Yeah, the regulation, you are talking about regulation, any change in the input, but you have a buck converter, na? Which, I mean, I'm assuming you have a very fast controller which can regulate the output voltage, 5 volt, no problem. Any problem you think you might encounter as a user? No one? Seriously, no one? Okay. Let me first draw it so that you see the problem clearly. Yeah, I'm talking about this circuit. Hypothetically, if this works, the buck converter works, do you want to use it at your home? Can you use it? You won't, because if you use this, there are these two terminals, this is plus, this is minus 5 volt. You are very used to, just that adapter or the if you see the charger, anyone has a charger cable? Okay. So if you see this side of the cable, right, if you see this side of the cable, this outer shell is exposed, right, and we are used to touching it without getting bothered. So this gets plugged in, we touch it, right. Now if you touch this, the negative or the outer part of the connector, right, you don't get any shock, huh? You don't get any shock. But in this case, you would get a shock, because this is a rectifier circuit. Sometimes this neutral will be connected through this diode to the negative bus. Sometimes the phase will be connected through this diode to the negative bus. So sometimes this part is connected to the neutral, sometimes this part is connected to the phase. Whenever it is connected to the phase, you would get to 30 volt shock if you touch it, right? So you cannot, sometimes you require isolation for this purpose, right? So even if theoretically this would have been possible, that would not have been a good idea to have a buck converter based this, right? Because now we are used to it, right? I mean, we don't expect this part to actually give any shock. So the only way forward is use a transformer, right? It gives you isolation, it gives you smaller size. If it's high frequency transformer, it gives you reasonably good efficiency as compared to using a buck converter for a large attenuation. And of course, if you want to do boost, there is no other option left, right? So we use something called as a flyback. Flyback. One disclaimer before we move forward, please don't ask me why it is called flyback. I have no idea. You can try to search. If you find a convincing answer, share it with us, all of us. Right? I remember you guys used to ask me in the last lecture about some nomenclature, right? What was that? I forgot. But there was some questions which this guy who is busy with the phone used to ask and so on about the naming thing, right? So this one, I'm serious. I have, very limited idea about why it's called flyback. But you should try to find out. Alright, first you can draw the circuit. I will explain you how it operates. Okay. So, as someone suggested that, if you want to do a DC to DC, you can invert it, high frequency, pass it to a transformer, it will step it down, then you rectify it, right? and you can do it in a very literal way, right? I mean, just the way it is said. You know, full bridge inverters, right? You have learned it somewhere. There are like this kind of a structure, right? This one you have seen somewhere. We will read more about it, but you know a basic idea, right? So you can supply a DC voltage, invert it, high frequency, put a transformer, and then put a diode rectifier. That's a very exactly one-to-one mapping of someone suggested. This is also doing the same thing, but it's doing it in a little bit different way, but the basic principle is more or less the same. Plus what this guy is doing is it's saving you in terms of the number of switches, the number of components, right? So maybe this would be preferred way of doing it if it's a very high power system. This would be a preferred way of doing it if your system is very low power, compact, such as mobile chargers, right? But this is also basic principle remains more or less the same. So let's try to understand this guy here. This transformer is, if you assume it to be ideal transformer, let's see what happens. So switch S, on, off. Let me call it V1, and now this dot is in this direction, so this would be then plus, this would be minus, and reference, let me call it as V2. Is that okay? Or do you want the plus minus to be same? Then I can, I think this is fine. So if I write V diode is nothing but equals to minus times V2 minus times VO. Is that okay? Is this equation fine if you write a Kirchhoff's voltage law here? If I define V diode with this reference polarity, it's nothing but equal to minus times V2 minus times VO. Any doubt in this equation? This is VD. Is that okay? Kirchhoff's voltage law, you start from here, assume this is ground, 0, minus V2 plus VD minus V0, sorry, yeah, 0 minus V2 minus VD minus V0 is equals to 0. So you can take VD on the other side. Is that okay? I can write another equation which is V2 is equals to N2 by N1 times V1, right, which is this transformer. So V2, the dot side positive, is equals to V1 dot side positive multiplied by the turns ratio, which is N2, maybe this will, so the transformer has a turns ratio of N1 is to N2. So far, is it okay? Any doubts? Alright. So if I turn the switch on, what is V1? If I turn the switch on, and don't answer it, we will go one by one. I'm thinking which side, maybe we'll start from this side for a change. If I turn the switch on, S is on, what is V1? Can you see this circuit? Ah, okay. If the switch S is on, what is V1? Just look at the primary side, right? Transformer is ideal. Just apply the Kirchhoff's voltage law. If S is on, what would be V1? Vin. Alright. Okay. If V1 is V in, I know V2 would be N2 by N1 times V in. What would be the diode voltage VD? At least would it be positive or negative? VD, would it be positive or negative? VD, assuming output voltage is positive, right, 5 volt. which we want to create. Would the VD be positive or negative? Negative, because this is also V0 is positive, V2 is also positive, both comes with a negative sign, so total has to be negative. So VD is, let's say, somewhere here, negative. If VD is negative, this diode is off. Alright? Good. Then when the switch turns off, subsequently S turns off, what would be V1? If the switch S turns off, what would be V1? It's open circuit, right? It's open circuit, this is an ideal transformer, no current flows through it, it's 0. What would be V2? 0. Would the diode be forward bias or reverse bias? What is VD now? What is VD now? This is 0, this is still 5 volts, so VD is still minus 5, so diode is still off. So, is that okay? Earlier it was more negative, now it's maybe less negative, but nevertheless negative. Any questions so far? Yes. There is no inductor there. We have considered ideal transformer. So there is no inductor. Where is the inductor? I didn't put any inductor. Yeah, we will have a magnetizing inductor, sure. That's good. Any other thoughts? I'll answer your question, or rather I'll take it forward. But any other question or any other thoughts on this circuit? Why? Why do you have diode, right? Yeah. So this is always off, so this is as good as not there. So how is the power getting transformed from input to output? It's not. So this is not a converter, it will not even work, right? If you put this, nothing will happen. Your output voltage will not get created, absolutely nothing. And for it to work, you need some form of inductor. If you remember the buck converter, right, what was it doing? Was storing energy in inductor and then giving it to the output. Same thing was happening in boost also. Here there is no inductor. So of course, seems a bit unlikely. So now consider the magnetizing inductance of the transformer, which is there, it's just that I didn't draw it before. This is anyways there, right? If you have a transformer, you can never have it ideal. So now you have a magnetizing inductance, and this part which I have drawn is the ideal component of the transformer. But the overall it's a real transformer which has a magnetizing inductance. Is this okay? So this small part is the ideal transformer. The whole thing is the actual transformer which has a magnetizing inductance LM. Let's redraw the waveforms now and let's see what happens. Alright. Any question, any doubt so far? Now again we'll do the same thing. S is on, right? S is on from 0 to DTS period. So when S is on, what is V1? In this new case, I will keep erasing it and keep drawing the new waveforms, right? So you have to tell me when S is on, in this case, when you have a magnetizing inductance, what would be V1? V1 would be V in, okay, so I think this we have drawn it correct. What would be VD? What would be VD? Will it be negative or positive at least? It will still be negative. So I think this also we have drawn correct, there is no change here. We have drawn, now there is an inductor, so I also want to draw the inductor current. What will happen to the inductor current? What will happen to the inductor current? What will happen to the inductor current? In this case, what will happen to the inductor current, ILM, when the switch is on? Next person. It will positive, but what will be its nature? Going down, going up, constant, going up, okay. So your inductor current, voltage across the inductor would be V in, which is equals to L di by dt. So di by dt will be positive and it will be equal to V in by L. So your slope will be positive. So your inductor current will go like this. Is that okay? Is that fine? Inductor current will rise because V equals to L d/t. Good. So I think we are from 0 to dTs we have drawn all the waveforms. So far so forth. What happens from dTs to Ts period now? Switch is off, S is off. What happens to V1? Switch is off, what happens to V1? Negative. V1 is negative. Okay, how many of you say V1 is negative? Raise your hand. Oh, quite good number of people. Why are you saying negative? Negative is the right answer. Question is why? Okay, next person want to try. Why negative? Inductor would have. But yeah, so we are talking about inductor voltage only, right? V1 is the same as transformer voltage as inductor voltage, right? But why would the voltage be negative? Next person. Okay. Okay. Yeah, more or less. One more person who raised the hand from this side. V1 will be negative. Okay. Okay. Anyone wants to add any sentence to this? Why would V1 be negative? Okay. That's not the cause, that is the effect. Because V1 is negative, current will be decreasing. Right? Certainly V1 would be negative, current would be decreasing, all of us know that, but that's the effect of V1 being negative, right? What is the cause of V1 being negative? In inductor current will? It will continue to flow, okay. It will flow like this, okay. No, that is reference. Reference is anything. Why is the actual voltage negative? We are talking about the reference voltage convention. That doesn't matter. Always inductor current can flow one to another side. Voltage could be positive, voltage could be negative. Yeah, you are right. So what he is saying is current cannot change instantaneously, and that is where the clue lies, right? But you just have to see the whole picture.
On the left side straight out of the dot. So on the right side of the transformer, the current will be flowing into the dot. So the voltage across the resistor axis will be positive. So V2 is negative.
Okay, so I think that's a good progress. What he's saying is current has to continue to flow, inductor. So current will leave the dot, ideal transformer. On the other side, current would enter the dot, right? Because in ideal transformer, there is no energy storage, there is no loss, right? So input power is equal to output power. So if current is leaving this dot, current has to enter this dot. If current has to enter this dot, the way it can flow is like this, right? Therefore, this diode is now forward bias. If diode is forward bias, what is V2? V2 is equals to, if this diode is forward bias, voltage drop is almost 0. If you write Kirchhoff's voltage law here, V2 will be equals to, if output is let's say 5 volt, V0 is 5, V2 will be equal to minus 5, and therefore V1 would be equal to minus 5 times N1 by N2. So V1 will be negative. Is that okay? Don't worry, I will repeat it once again if you have missed any part of it. But first let me draw. And VD will be almost 0. D will be on. Diode and since the voltage will be negative, the current will fall and come to this point. So why would you assume V1 to be constant? So only from 0 to DTS. After that it is negative, na? Oh, why is negative constant? We'll come to that. Okay, let me just explain it once again. Maybe you can note down the waveforms. I'll repeat it once again. So you can look at it that inductor current has to be continuous, right? So if inductor current is continuous, the only way inductor current cannot flow through the switch is open. So the only way for the inductor current to flow through is in this loop, right? It cannot flow through the switch, it can only flow through this loop. If it flows through this loop, it leaves the dot. That means for that to happen, the current must enter the dot. If current is entering the dot, the only way to happen is if the current is flowing in this direction. That means the diode is forward biased. If diode is forward biased, V2 is equals to minus V0. Reflected with the turns ratio, V1 will be equal to N1 by N2 times minus N1 by N2 times minus of output voltage, and therefore V1 would be negative, and therefore this current will start reducing. Is that okay? Any part you want to repeat? Anyone? Yeah, because it's an ideal transformer, right? This section is the ideal transformer. So in ideal transformer, input V1 I1 should be equal to V2 I2 all the time, right? Voltage ratios is N1 by N2. Current ratio is therefore also N1 by N2. If the current is entering one positive voltage, it has to leave one positive voltage so that the input power is same as the output power. Any question? Any doubt? बोल भाई तो उदास क्यों है? नहीं? Any question? Sure. So now at least this circuit will operate, because when you close the switch, the inductor current builds up. When you open the switch, the inductor current reduces and it indirectly flows into the output capacitor, right? So you have, now you can see at least there is a power electronic converter which could be, operating in this fashion. And if you remember, just some time back we were talking about, right, it's still the same basic principle. You are inverting the voltage, you are rectifying it. You see V1, how does the V1 look like? V1 is an AC voltage, right? So somehow through this, just a single switch, you are able to invert the voltage, create V1, which is an AC voltage, which creates V2, which is also an AC voltage, and then using a single diode, in a way you have rectified it and you have created the output. You can look at it that way, or you can look at it the way we have just now, gone step by step in terms of operation. But mota, the principle is the same, that you are in a way somehow inverting the voltage at high frequency, stepping it up or stepping it down and then rectifying it. Any doubt? Any question? No question? After the switch off, voltage is negative, so the current has to fall, right? V equals to L di by dt. So voltage is negative, means di by dt has to be negative. Okay? So this inductor is usually not an external inductor, this is the magnetizing inductor of the transformer itself. So if you see physically a flyback circuit, this is just one package, right? This is just one thing, it's not two things, this is just one thing, right? This is just one thing. And you have a switch and a diode and an output capacitor. So very simple circuit, right? Very, very simple circuit, and therefore very popular in low power applications, right? Can you draw the transformer flux? Can you draw the transformer flux? This unit is just a transformer, right? Can you draw its flux, which will be inside? Can you draw its flux? Can you draw its flux? Will mirror IL. Okay. Transformer flux. Transformer flux same as current. Transformer flux is same as IL. Why? Okay. So VL is equals to LdIL by dt, which is nothing but E is equals to N1 times d phi by dt, and therefore L times IL upon N1 is nothing but the flux, right? And therefore the flux would have the same shape. Of course, the magnitude would get multiplied, but the same shape as that of the current. So your flux would also look like this, which is not just true for this converter, but which was true for the inductor we used in buck converter, the inductor we used in boost converter also, right? Because everywhere we used an inductor where there was actually a flux, right, and which was related to the current, it was proportional to the current. In this case, the flux waveform, why we are drawing in this case, why we have not drawn before is, before it was very clear there is a separate inductor, uska ek current hai. In this case, this inductor is not there physically, right, it's merged. So if I tell you that can you physically observe the inductor current, you cannot, right, because this is inside. If you measure this current, it will be this plus this current, right, you will not get the transformer current, and therefore in lot of books, lot of explanation, people would explain using the flux instead of explaining it using the current, and that's why this flux waveform has some sort of significance here. But nevertheless, the flux waveform was there in buck converter also, boost converter also, right, because there is also an inductor with a core with n number of turns. Any question? Okay, then what we do is, we stop now. Next lecture, what we'll do is, we'll derive the input-output voltage relationship for the flyback converter.